In this video, we're going to talk about composition of functions and the difference quotient. Composition of functions is a way to create a new function by combining two existing functions. And the way it's done is by substituting one function into another. So I write it as f compose g of x. And when I do the composition, I substitute the function that is listed second into the first function. In this case, I substitute g of x into f of x. And there's this layering effect where I'm applying two functions, one right after the other. So if you think of plugging a number in here for x, I would need to work from the inside out. I would plug a number in here, and then I would take that number and plug it into the function g and get g of x out as a result. And then I would take that result and plug it into the function f to get my final answer. So it's a two-step process, and that's when the composition can be useful if you want to take two separate formulas or two separate calculations and layer them into one function. Okay, so I've chosen one from your book. Here are the two functions that we are given. We're asked to find f compose g and g compose f. So I always start with the definition. F compose g of x is f of g of x, which means I'm going to take the function g, this negative 2x plus 1, and I'm going to do a substitution, and I'm going to substitute it into the function f by replacing the x that I see in both places here. You could go there directly, or you could kind of ramp up, I guess. So g of x is negative 2x plus 1. Sometimes I like to write this because this helps me remember what I'm substituting. Now I'm going to put this into the function f everywhere where there's an x. So I'm going to take the x out, and I'm going to use negative 2x plus 1 as the input in place of the x. So that's really the crux of the idea that we're doing, is this step. The rest is just making it look nice and simple. So from here, I would want to expand this as much as I can. So I'm going to need to FOIL two copies of negative 2x plus 1 multiplied together so that I can square it. I can distribute my negative 3 to get plus 6x minus 3 plus 2. Let me go ahead and FOIL these together. That'll give me 4x squared. On the outside, I'll have plus 2x. Oops, just kidding. On the outside, I'll have minus 2x, and on the inside, I'll have minus 2x. So I'll have minus 4x plus 1. And now I'm going to multiply all of that by 2. So that's going to give me 8x squared minus 8x plus 2 plus 6x minus 1. So altogether, this new function will be 8x squared minus 2x plus 1. Oops. And so this is f compose g of x, right? This is what I was trying to find, and this is what I got as my result. So I took those two functions that I was given in this problem, and I layered them together, and this is the new function that was the result of that. Okay, so it's very common to do this layering in both directions or in both ways. So the order does matter, whether I do f compose g or g compose f. Right? Those are not always the same. So it's very common as far as exercises go to try to do both of them. So let's do that. So now we're going to reverse the roles of G and F. And we're going to try to find G compose F of X. Again, I always like to start with the definition. So this means G of F of X, where I'm substituting F of X into the function G. Here is F of X. So I'm going to take all of this and put it in the place of X. So I'm going to take the X out and replace it with F of X, like a substitution. Okay, so just like before, if you want to identify what you are substituting, you could write this preliminary step. It's sort of extra and definitely not required. Okay, and I want to plug that into the function G. The function G looks like this. I'm going to take X out, and I'm going to put F of X right in that spot. And like we said before, really this is the key step right here, is being able to do that substitution. The rest is just making it look simple as possible. So this would be negative 4x squared plus 6x minus 4 plus 1. And if I simplify it out, it will be negative 4x squared plus 6x minus 3. I was looking for G compose F of X, and this is the new function that I've created. I always like to point out, like we said just a minute ago, that the order does matter. So notice I did not get the same function here. These are not always equal. There is a special circumstance when they are equal, and that is when G and F are inverses of one another, or opposite, containing opposite operations. In that case, they will match, but every other time, unless it's a coincidence, they are not likely to match. Okay, so that gives you a little bit of an idea of what composition is. I want to add to that the idea of the average rate of change. So we said that we were going to talk about composition and the difference quotient. The difference quotient kind of piggybacks off of this idea of the average rate of change. So I always link those two together because their meaning is very connected. So the average rate of change extends the idea of slope from not just a line. It allows us to approximate the slope of a curve. And so we have a formula here for the average rate of change. Really, this is the same as the slope formula. For each y, I'm writing it with function notation. So instead of using y, I think of f of x. That's kind of the idea here. So we're maybe a and f of a is my first point, and b and f of b is my second point. And we could even write it out that way. 2 points, a comma f of a. F of a just means the y value I get when I use a as my x. And then b comma f of b. And so the average rate of change is just mirroring the slope formula. Okay, and then below we said the average rate of change calculates the slope of what's called a secant line, and a secant line is a line joining 2 points on a graph. Okay, so let me give you an example of that. This is an example that I have used in the past from a book that I was using at that time. It's not a perfect example, so we'll go ahead and go through with the example, and then I usually talk about why this is not the greatest example and how it could be better maybe, and then we'll relate that to the difference quotient. Okay, so in this example, for the functions shown in the figure, find the average rate of change, and it gives us 2 points. I went ahead and drew in the secant line. The secant line is the line joining those 2 points. And so I want to find the slope of the secant line, and that's going to be the average rate of change. Okay, and I'm going to abbreviate average and then ROC for rate of change. Basically, I'm going to use these 2 points to calculate the slope. And that's not something that we're familiar with that, right? So I can do -4 minus 2 over 2 minus -1. That's going to give me -6 over 3 or -2. So the average rate of change here is -2. And so really that's the slope of this secant line. Okay, so now let me talk a little bit about why this is not my favorite example. I probably should pick a new one at some point. We use the slope of the secant line to approximate the slope of the curve. So usually we have a curve and we pick 2 points that are a little bit closer together so that the secant line is close to the curve. And that way the slope of this line will be closer to the slope of this curve. These 2 points are not really close together. It would be really more appropriate to pick maybe 2 points on this, at least the same side of this parabola, right? So maybe I pick 2 points here and I'll do a dotted line so you can see it better. A dotted line kind of through here. This would also be a secant line. It passes through these 2 points. And the slope of this line would more closely match with the slope of the curve kind of in between those 2 points. And it is an average, and so it's an estimate. But we have ways of making our estimate better and better, and so that's kind of where we're headed with this. Okay, so that's the idea of the average rate of change. We have 2 points on the curve, and we estimate the slope of the line to be close to the slope of the curve. Okay, so now let's look at the difference quotient. The difference quotient is the average rate of change between 2 points that are very close together. So think about the picture we just drew. We picked 2 points on this curve that are very close together. And we're looking at the slope of the secant line between them. Okay, so the 2 points we're picking, first of all, we're going to use x comma f of x. And just like before, f of x here is the y value I get when I use this particular x. And then we want these points to be really close together. I drew them kind of far apart so we could see it well, but say this is zoomed in on a microscope or something and they're actually really, really close. So then let's say x were like a 2 and h here, I'm going to write this as x plus h, were like a 0.01. So this would be like between 2 and 2.01. I want them that close, maybe even closer. Then my approximation is really going to be close to the slope of the curve. Okay, so that's kind of the idea behind the difference quotient. These 2 points, the x and x plus a little bit, or x plus h, are close, and so we're using the coordinates of these 2 points to calculate the slope of the secant line, which is the average rate of change. This would be the formula that we get if we plugged those things into the average rate of change, right? Think of y2 minus y1 over x2 minus x1. Here in the denominator, we have positive x and negative x, so those are going to cancel each other out. And so the final formula just has an h down there in the denominator. This is a formula that I usually provide for you, but I always like to explain where the formula is coming from, and this one is based on that average rate of change. Okay, and the difference quotient is a baby step in the direction of the derivative. So we're not to calculus yet. The derivative calculates the slope of the curve at whatever point we want, can give us a formula for that, so we can pick the x value where we want to find the slope of the curve, since it's constantly changing, unlike a line. Okay, so we're not quite there yet, but practicing this will be a very good prerequisite skill to have when you start into calculus, because this is kind of where the derivative is born from. Okay, so now we're going to take some time to calculate the difference quotient for a couple different types of functions. I always start with a function that's a line, just so that you can kind of get an idea for how it's going to look. And this one is sort of self-checking because it's a line, it's not a curve. So that means when I find the difference quotient, which is the slope of the curve, I'm really just going to get the slope of this line. And I already know about lines. So this is in that mx plus b format. The slope here would be -3. So I already know I should go through this process. I should get the slope, which will be -3. I don't want to give away the answer, but really the practice here is not for the answer, it's for the process. Okay, if you wanted to break the process up into 2 steps, you could first calculate the f of x plus h part. And this is like a substitution. It's like a composition where we're substituting in the x plus h. So let's do that. So everywhere where there's an x in my function, I'm going to remove the x and replace it with x plus h. And we might as well go ahead and make it look as simple as possible by distributing our -3. Now we're ready to put together the difference quotient. So I have f of x plus h, which is what we just calculated, -3x minus 3h plus 1. I always put it in parentheses because I'm going to be subtracting the original function, which is the -3x plus 1. And one really important step that you don't want to miss is that we will need to distribute that negative. So I can take the parentheses off once I have distributed the negative. I always say some nice canceling should happen at this point. So the -3x and +3x, those are going to add to 0. +1 and -1, those are going to add to 0. I'll be left with -3h over h. The h's are going to cancel this time. And so my final answer, just like we said at the beginning, will be -3. So if you want to do some practice problems on your own for this process, an equation for a line is a good starting point because it's self-checking. I know that I'm going to get the slope, and it doesn't matter what equation for a line you use, you should always get the slope when you calculate the difference quotient. Okay, let's try a couple more. This one is also from your book. We could do the same couple of steps here if you wanted to break it up into 2 parts. We could start by doing f of x plus h. And like we said, that's sort of like a composition, so we're going to be substituting x plus h in the place of x. So instead of an x squared, I'm going to make it x plus h squared. Instead of a -3x, I'm going to make it -3 times x plus h. Notice I did not take my function and just sort of tack an h onto the end. That's a pretty common mistake to make, so don't let yourself fall into that trap. Okay, since I'm squaring this, I'm going to write out 2 copies. I'm going to go ahead and distribute my -3. And then I'm going to use FOIL to multiply these two copies together. Next, I'm going to distribute my 2. I always expect that some of these will be combined, but in this problem, that's not the case. So that's fine. All right, so this is my f of x plus h, this gigantic thing here. Now I'm ready to make the difference quotient. The difference quotient is f of x plus h minus f of x all over h. So I want all of this and again, I'm putting in parentheses, and I'm going to subtract the original function that I was given at the beginning of this problem. All of that over h. I don't want to forget to distribute this negative. That's why I put the parentheses. Okay, this is the point where some nice canceling should happen. I've got 2x squared and negative 2x squared. They add to 0. Negative 3x and positive 3x add to 0. 2 and negative 2 add to 0. Everything that's left should have an h in it so that I'm free to divide by h. And I'm going to divide all 3 parts by h. So my final answer will be 4x plus 2h minus 3. We're not going to do this part, but the next step in finding the derivative would be to let the h go to 0 so that those 2 points that are really close, h is like the distance between them, and we're bringing them as closer and closer together as we possibly can so that we can find a formula for the slope at one single point on a curve. Okay, how about one more? This one is also from your book, and we can break the process up into those same 2 steps. The first step being f of x plus h. So right where there's an x, I'm going to put in an x plus h. And then I'm going to use that to make the difference quotient. And I'm going to subtract f of x plus h minus f of x all over h. This time this gives us a fraction within a fraction. Okay, so maybe the first step in dealing with something like this is to try and get the denominators of these 2 fractions on the top the same. I need a common denominator. So I think I'll use LCD, my least common denominator. It needs to have a 2 because that's represented. Only 1 though because they share a 2. It needs to have an x, and it needs to have an x plus h. Okay, so in order to have that denominator for the first fraction, I need to multiply the top and bottom by x. You need to in order to have that denominator for the second fraction, I need to multiply the top and bottom by x plus h. So that is going to give me x over 2x times x plus h minus, I'm going to put it in parentheses, x plus h over 2x times x plus h divided by h. Okay, and now I'm going to do a couple things at the same time. Rather than writing this as a giant fraction over h, dividing by h is the same as multiplying by 1 over h. Just like dividing by 2 is the same as multiplying by a half. It's the same idea. So I'm going to bring that out to the front so it looks a little less menacing, I guess. Okay, and then I want to subtract these. So really this is x minus x plus h all over the same denominator. And I want to distribute the negative. So that's really x minus h. X minus x, that they're going to add a 0. So I get 1 over h times negative h over 2x times x plus h. And I can cancel out the h because I'm dividing by h. 1 in the top and 1 in the bottom. 1 for 1. So I end up with my difference quotient being negative 1 over 2x times x plus h. Well, I hope this gave you a good explanation of what the difference quotient is, what it calculates, where it's leading to, and how to operate with it. It's going to take some practice if you haven't done this before, so I hope that you'll take the time to practice this. I really think it's going to pay off for you in calculus. All right, good luck.